Today we're going to look at prime decomposition. Prime decomposition, or prime factorisation, involves writing a number as a product of prime numbers. This can be useful later on because we can see when we look at two different composite numbers and their prime factorisations, we can compare them and see which ones have different prime numbers in common. A factor tree can be used to show the prime factors of a composite number. But if we have a look at decomposing 12, so 12 is a composite number, we can have a look at its prime factors. So if I expand 12 out and only multiply it by primes, so 2s and 3s are primes. 12 is the same as 4 times 3, but 4 isn't prime. 2 times 2 makes up 4 though. So 2 times 2 is 4, times 3 is 12. So these are all prime numbers. This is the prime factorisation of 12, or the prime decomposition of 12. 2 to the power of 2 times 3. You can see we use the power notation to make it more compact, make it easier to see and read. So this factor tree, the way we can use the factor tree is going to be helpful for larger numbers, and it helps us break it down again and again and again into smaller and smaller numbers to make sure that we end up with all of the primes. So what we need to do first is we need to write the composite number at the top of the tree and then draw branches down that multiply to give the composite number. So if we drew 12 at the top of the tree, we could compose it on the two branches of 4 and 3. 4 times 3 is 12. We need to then continue that pattern down and repeat until all the branches end in prime numbers. We can circle the prime numbers then to make sure that they are prime, to visually show us that they are prime, and then we show the initial composite number as a product of these primes. We write it as a number sentence, as an expression. And then lastly, we simplify using powers. So if we have a look at 48, I can draw two branches down to multiply 48 by two numbers, and those two numbers are going to be 4 and 12. I've just chosen 4 and 12. I could have chosen 2 and 24. It does not matter which ones you start with, because as you keep branching down and down and down, you get the same prime numbers. So 4 and 12, both not primes. They're both composite numbers. So I'll leave them as is and branch them again. So branching 4 down, the only thing I can multiply two numbers by to get 4 is 2 times 2. I could branch 4 and 1, but that would not make sense, because we keep going forever and ever if we keep multiplying by 4 and 1. And anything multiplied by 1 is itself anyway. So we're looking for factors that aren't 1, obviously. So 4 is 2 times 2. We can circle both of those 2's to say, okay, yep, they're prime. We can stop there. We don't have to branch those anymore. 12, once again, we've seen that 12 can branch into 4 and 3. So 3 is a prime, I can circle that and don't need to worry about branching that one off anymore. And 4 we know is 2 times 2, so I've branched that down again and circled the 2's. You can see we've completed now. We can't go any further because we don't have any more composite numbers that can mean any more branches. So here we've got 4 2's rather, and 1 3. So that's 48 is equal to 2 times 2 times 2 times 2 times 3. A very long number sentence indeed, you can see. So let's compact it and simplify it using our power notation. So 2 we've multiplied 4 times, that's the same as 2 to the power of 4, and we've multiplied by 3. So 48 is equal to 2 to the power of 4 times 3. Got an example for you here now. So let's look at this one, expressing the number 504 in prime factor form. So we're going to be doing the same thing with this very large number now, 504, converting it to the prime factor form, which is going to be a little bit challenging. So it's best if we use the prime factor tree, our factor tree, to work it out. So if we start with 504, there are a whole lot of numbers that we can multiply to get 504. I find it easier if it is obviously an even number. If it ends in an even number and is definitely going to be even, dividing it by 2 until you can't divide by 2 anymore, I find is the easiest because it's very easy to divide a number by 2. So 504 is the same as 2 times 252. Okay, so 504 divided by 2, we're left with the 252. I can divide that by 2 again, and once I've divided by 2, I can circle that because 2 is a prime number. and I get 126. 126 is prime again, even again rather, so I can divide it by 2 again. So, and that's 2 times 63. Now 63 isn't an even number, so I need to find a number, prime number, that I can multiply this by. It'll be easier to find if I can find a prime number to divide this by. So I can see that if I divide 6 by 3 and 3 by 3, it'll go evenly into both of those. It'll break up evenly, so it'll be divisible by 3. So 63 divided by 3 is 21. 3 times 21 is 63. Then I'm left with 21, and 21 can be the product of 2 primes. Can only be the product of 2 primes. 3 times 7. Okay, so they're my final branches. So on tips of all my branches, I've got 1, 2, 3 2s, 2 3s, and a 7. So that means 504 is equal to 2 times 2 times 2, 3 2s, times 3 times 3, times 7. So we can simplify there using power notation. 2 times 2 times 2 is the same as 2 to the power of 3, and 3 times 3 is the same as 3 to the power of 2. And then we multiply by 7 at the end there. So our prime decomposition of 504 is 2 to the power of 3 times 3 to the power of 2 times 7.